You know, I want to start with something that has genuinely kept me awake at night. And I don't say that as a figure of speech. I mean, literally lying in bed, staring at the ceiling, turning an idea over and over in my mind because it's so strange, so counterintuitive, so deeply unsettling to everything we thought we understood about reality. Here's the question: what happens at the center of a black hole? Now, you might think we know the answer to this. Black holes have been part of our scientific vocabulary for over a century. We've detected them, photographed them, observed their effects on surrounding matter. Surely by now we understand what's inside them. But here's the thing. For decades, the honest answer from physicists has been, we have no idea. Not, we have a pretty good guess. Not, the evidence points toward. Literally, we have no idea. The mathematics breaks down, the physics fails. Our best theories, the ones that have correctly predicted everything from the behavior of electrons to the expansion of the universe, they give us nonsense when we ask what happens at the very center of a black hole until now. Because over the past several years, a remarkable convergence of ideas from quantum mechanics, general relativity, string theory, and a field called loop quantum gravity has begun to paint a picture that is, frankly, astonishing. And what that picture shows is something that I think will fundamentally change how you think about black holes, about the universe, and about the nature of reality itself. The bottom of a black hole may not be a dead end. It may be a doorway to another universe. Let me show you how we got here. First, let's establish what we thought we knew, because the traditional picture of black holes is already strange enough, and understanding why it fails will help you appreciate why the new ideas are so revolutionary. A black hole forms when a massive star, something at least 20 or 30 times the mass of our sun, exhausts its nuclear fuel and can no longer support itself against gravity. The core collapses. And if the star is massive enough, that collapse doesn't stop at any intermediate stage. It just keeps going. The matter gets compressed, denser and denser. The gravitational field gets stronger and stronger. Eventually, the gravity becomes so intense that even light cannot escape. That boundary, that point of no return, is called the event horizon. Now, the event horizon is not a physical surface. It's a mathematical boundary, the radius at which the escape velocity equals the speed of light. Cross the event horizon and you're trapped. Nothing you can do, no amount of thrust, no clever maneuvering will ever get you back out. You are doomed to fall inward. And here's where it gets weird. According to Einstein's general theory of relativity, the theory that describes gravity as the curvature of space-time, that inward fall doesn't stop, ever. The matter that formed the black hole, plus anything that falls in afterward, all gets compressed into a single point of infinite density. That point is called the singularity. Infinite density, infinite curvature of space-time. All the mass of the black hole concentrated into a point with zero volume. Now, I want you to really think about what that means. A point with zero volume, that's not small, that's not tiny, that's literally zero size. And yet, it contains mass, perhaps millions or billions of times the mass of our sun in the case of supermassive black holes. Does that make sense to you? Because it doesn't make sense to me, and more importantly, it doesn't make sense to the laws of physics. Here's the problem. Saying that the singularity has infinite density is not actually a prediction. It's an admission of failure. When a physical theory predicts infinity, it's telling you that the theory has broken down, that you've pushed it beyond its domain of validity, that something is missing from your understanding. Think about it this way. If I told you that the temperature tomorrow would be infinity degrees, you wouldn't think, wow, it's going to be really hot. You'd think, something is wrong with your weather model. Infinity is not a physical quantity. It's a mathematical artifact that appears when your equations don't capture what's actually happening. The singularity at the center of a black hole is exactly this kind of artifact. General relativity predicts it because general relativity doesn't know about quantum mechanics. It treats space-time as smooth and continuous, divisible forever into smaller and smaller pieces. But we know from quantum mechanics that this can't be right. At sufficiently small scales, the Planck scale, about 10⁻35 meters, the smooth fabric of space-time must give way to something else, something granular, something quantized, something that our current theories don't fully describe. The singularity is where general relativity is screaming at us, I don't know what happens here, I need help. And for decades, we couldn't provide that help. We had quantum mechanics, which brilliantly describes the behavior of particles and fields. We had general relativity, which brilliantly describes the behavior of gravity and space-time. But we didn't have a quantum theory of gravity, a theory that could describe what happens when quantum effects and gravitational effects are both important, as they surely are at the center of a black hole. That's been the holy grail of theoretical physics for nearly a century. And while we still don't have a complete theory, we've made remarkable progress. Progress that's now allowing us to peer for the first time into the heart of darkness. Let me tell you about an idea that has emerged from a field called loop quantum gravity. It's one of the leading approaches to quantum gravity, and it has something remarkable to say about black hole singularities. The basic idea of loop quantum gravity is that space-time itself is quantized. Just as matter is made of atoms and light is made of photons, space-time is made of discrete units, tiny chunks of volume and area that can't be subdivided further. These chunks are incredibly small, about 10⁻105 cubic meters, but they're not zero. There's a minimum possible size, a floor below which you cannot go. Now, think about what this means for a collapsing star. In classical general relativity, the collapse continues forever. The density increases without limit, and you end up with a singularity. But in loop quantum gravity, that can't happen. When the matter gets compressed down to the Planck scale, it runs into the granular structure of space-time itself. It can't compress any further. There's a floor. And here's where it gets really interesting. The calculations suggest that when matter reaches this maximum density, something extraordinary happens. The gravitational attraction that's been driving the collapse reverses. Let me say that again, because it's crucial. At the center of a black hole, according to loop quantum gravity, gravity stops being attractive and becomes repulsive. The collapse bounces. This is called the Planck star scenario, or sometimes the black hole bounce. And its implications are staggering. Imagine you're a particle of matter falling into a black hole. You cross the event horizon, you're pulled inward by the intense gravitational field. Faster and faster, denser and denser, you're compressed with all the other matter that's fallen in before you. In the classical picture, this ends in annihilation. You hit the singularity and, well, we don't know. The equations give infinity. Presumably, you cease to exist in any meaningful sense. But in the loop quantum gravity picture, something different happens. You reach the Planck density, the maximum possible density, about 1096 kilograms per cubic meter, and the collapse stops. Gravity becomes repulsive. The matter bounces. And where does it bounce to? This is the mind-bending part. The calculation suggests that the bounce creates a new region of space-time, a region that is causally disconnected from the universe you came from, a region that, from the inside, looks like an expanding universe, another universe, born from the heart of a black hole. Now, I can hear you thinking, wait, Brian, that sounds like science fiction. How can there be another universe inside a black hole? Wouldn't we see it? Wouldn't something come back out? And these are exactly the right questions. So let me explain why this scenario, as wild as it sounds, is actually consistent with everything we observe. The key is the event horizon. Remember, the event horizon is a one-way membrane. Nothing that crosses it can ever come back out. Not light, not matter, not information. From the perspective of the outside universe, whatever happens inside the black hole stays inside the black hole. So if the matter bounces at the center and creates an expanding region of space-time, that new space-time is trapped behind the event horizon. It can expand and evolve and potentially develop its own stars and galaxies and maybe even life, and we would never know. We can't see past the event horizon. We can't receive any signals from that inner region. It's causally disconnected from us. From our perspective, the black hole just sits there looking exactly like black holes have always looked. But from the perspective of someone inside, if such a perspective is even meaningful, a whole new universe might be unfolding. Let me give you an analogy that might help. It's imperfect, as all analogies are, but I think it captures something important. Imagine you're watching a river that disappears over a waterfall. You can see the water approaching the edge, accelerating as it gets closer. You can see it tip over and vanish from sight. But you can't see what happens at the bottom. There's mist, there's a cliff blocking your view. You simply can't observe it directly. Now, you might assume that the water just crashes onto rocks and dissipates. That would be the classical picture, the singularity, the end of the road. But what if, at the bottom of the waterfall, there's a cave? And inside that cave, the water flows into an underground river system that eventually emerges somewhere completely different, a different continent, a different watershed, a different ecosystem entirely. From your vantage point above, you'd never know. The water would seem to simply disappear. But from the perspective of that underground river, a whole new journey would be beginning. That's something like what loop quantum gravity suggests is happening at the center of black holes. The matter that falls in doesn't just end. It bounces into a new region of space-time that's hidden from our view behind the event horizon. Now, I want to be careful here, because I've seen how ideas like this can be misrepresented. So let me be very clear about what we do and don't know. We do not have direct observational evidence that there are universes inside black holes. We cannot see past event horizons. We cannot send probes into black holes and receive data back. This is, at present, a theoretical prediction based on our best attempts to combine quantum mechanics and general relativity. What we do have is mathematical consistency. The loop quantum gravity calculations don't produce infinities. They don't break down at the center. They give finite, well-defined answers, and those answers describe a bounce rather than a singularity. This is a big deal. For the first time, we have a framework that can actually describe what happens at the center of a black hole without the equations blowing up in our faces. That doesn't prove the framework is correct, but it's a remarkable achievement nonetheless. And here's what I find most compelling. This isn't just one group of researchers with one speculative idea. Multiple independent approaches to quantum gravity, loop quantum gravity, string theory, asymptotically safe gravity are all converging on similar conclusions. They're using different mathematical techniques, different conceptual frameworks, different starting assumptions, and yet they're all suggesting that the singularity is replaced by something finite, and that something might be a connection to another region of space-time. When independent approaches converge on the same answer, that's usually a sign that the answer is right. But wait, there's more to this story. Because if black holes give birth to new universes, that raises a question that I find absolutely fascinating. What about our universe? Could our universe, this vast expanse of galaxies and stars and planets that we call home, could it have been born from a black hole in some other universe? This idea has been around for a while, actually. It was proposed in various forms by physicists like Lee Smolin and others going back to the 1990s. But the recent work on loop quantum gravity has given it new mathematical grounding. Here's the logic. If every black hole creates a new universe, and if our universe contains billions of black holes, then our universe is spawning billions of baby universes. And if our universe was itself spawned by a black hole in a parent universe, then we're part of a vast family tree, a cosmic genealogy of universes, giving birth to universes, stretching back how far? Infinitely far? We don't know. This is called the cosmological natural selection hypothesis, and it has some remarkable implications. Let me pause here and acknowledge something. This all sounds incredibly speculative. Universes inside black holes, cosmic evolution, a family tree of universes, and you're right to be skeptical. This is at the very edge of what physics can currently address. We're pushing into territory where our theories are incomplete, our data is limited, and our conclusions are necessarily tentative. But here's why I think it's worth taking seriously. First, as I mentioned, the mathematics is working out. For the first time, we have frameworks that can describe black hole interiors without singularities. That's a genuine advance, regardless of what the ultimate physical interpretation turns out to be. Second, the alternative, the singularity, is not actually a solution, it's a confession of ignorance. Saying there's a singularity is like saying we don't know. If we're going to make progress, we need to propose alternatives and see where they lead. Third, and most importantly, these ideas make predictions. Not easy predictions, not predictions we can test with current technology, but predictions nonetheless. And that means, in principle, they're scientific. They're not just philosophy. They're hypotheses that could be confirmed or refuted by future observations. For example, the black hole bounce scenario predicts that very old, very small black holes, the kind that might have formed in the early universe, could eventually explode as their bounces reach back out through the event horizon. We might be able to detect these explosions. We might be able to measure their properties and compare them to the theoretical predictions. That's science. Difficult science, patience requiring science, but science nonetheless. Now, I want to take you deeper into the physics, because there's a phenomenon related to all this that has puzzled physicists for almost 50 years, and that the new understanding of black hole interiors might finally resolve. It's called the black hole information paradox, and it's one of the most profound puzzles in all of physics. Here's the setup. According to quantum mechanics, information is never truly destroyed. If you knew the complete quantum state of a system at one time, you could, in principle, calculate its state at any other time, past or future. Information is conserved. But black holes seem to violate this principle. When something falls into a black hole, the information about what it was, whether it was a book or a rock or a dying star, seems to be lost. The black hole settles down to a state that's characterized by just three numbers: mass, charge, and spin. All the detailed information about what formed it, what fell into it, seems to be erased. This would be fine if black holes lasted forever. You could just say the information is inside the black hole, trapped but not destroyed. But in 1974, Stephen Hawking showed that black holes don't last forever. They radiate energy through a quantum process now called Hawking radiation, and they slowly evaporate. And here's the problem. Hawking's calculation suggested that this radiation is completely random. It carries no information about what fell into the black hole. So when the black hole finally evaporates completely, the information is gone, truly gone, destroyed. This contradicts quantum mechanics. It's a genuine paradox, two of our best theories giving contradictory answers about the same physical process. For decades, physicists have argued about how to resolve this paradox. Many proposals have been made. But the new understanding of black hole interiors suggests a resolution that I find particularly elegant. If black holes don't have singularities, if instead the matter bounces and flows into a new region of space-time, then the information isn't destroyed. It goes somewhere. It passes through the bounce and into the baby universe. From the perspective of our universe, the information is lost. We can't access it. It's behind the event horizon in a region we can never observe. But from the perspective of the universe as a whole, if we could somehow take a God's eye view that encompasses both our universe and all the baby universes, the information still exists. It's conserved, just elsewhere. This doesn't fully resolve the paradox, I should say. There are technical issues that physicists are still working through, but it suggests a direction. It suggests that the answer to the information paradox might be intimately connected to the answer to what's at the center of a black hole. And that's beautiful. That two of the deepest puzzles in physics might have a common solution. That's the kind of convergence that makes physicists think they're on the right track. So let me bring this first part of our discussion to a close by summarizing where we are. For decades, we've known that our understanding of black hole interiors is incomplete. The singularity predicted by general relativity is a sign of theoretical breakdown, not a real physical entity. Something else must happen at the center. Recent advances in quantum gravity, particularly in loop quantum gravity, but also in other approaches, are beginning to tell us what that something else might be. The calculations suggest that the collapse doesn't end in a singularity, it bounces, and the bounce creates a new region of space-time potentially, a new universe. This is still theoretical. We don't have direct evidence, but the mathematics is consistent. Multiple independent approaches are converging on similar conclusions, and the framework makes predictions that might someday be tested. If this picture is correct, black holes are not dead ends. They're not cosmic garbage disposals that destroy everything that falls into them. They're cosmic seeds, portals to new realms of existence, the birthplaces of universes, and that changes everything we thought we knew about what black holes are and what our universe might be part of. In the next part, I want to take you deeper into the physics of the bounce. What actually happens at that moment of maximum compression? How does gravity reverse? And what does the new universe look like from the inside? We're going to explore some of the strangest ideas in all of physics, ideas about the nature of space and time, ideas about the fabric of reality itself, ideas that I promise you will challenge everything you think you know about the universe. So we'd arrived at this extraordinary point where the center of a black hole, that place where our equations used to give us infinity, where physics itself seemed to break down, might actually be a doorway, a transition point where matter doesn't end but transforms, where one universe gives way to another. But I want to take you deeper now, because saying there's a bounce is one thing. Understanding what that bounce actually is, what's happening at that moment of maximum compression, what the physics is actually telling us, that's where things get truly mind-bending. And to understand the bounce, we need to understand something fundamental about the nature of space and time themselves, something that challenges intuitions you didn't even know you had. Let me start with a question that sounds simple but isn't. What is space? Now, you might think you know the answer. Space is the emptiness between things, the void in which objects exist, the stage on which the drama of physics plays out. But that's not what modern physics tells us. Einstein showed more than a century ago that space is not a passive stage. It's a dynamic entity. It can bend, stretch, warp, and curve. Matter and energy tell space how to curve, and curved space tells matter how to move. That's general relativity in a nutshell. In this picture, space is something. It has properties, it can be affected by what's in it, and can affect what's in it in return. It's not nothing, it's a physical thing, as real as any particle or field. But even this picture, revolutionary as it was, treats space as continuous, smooth, infinitely divisible. You can zoom in on any region of space and you'll find more space inside it. There's no bottom, no smallest unit, no pixel. Loop quantum gravity says this is wrong. Here's the key insight of loop quantum gravity, and I want you to really sit with it because it's profound. Space is made of discrete chunks. there's a smallest possible volume, about 10 negative 99 cubic centimeters below which you can't go. If you try to probe smaller scales, you don't find more space, you find nothing. Or rather, you find that the question, what's smaller, doesn't have a meaningful answer. This is not just a limitation of our measurement abilities, it's a fundamental feature of reality. Space itself is quantized, just like energy, just like electric charge, just like angular momentum. There are atoms of space. Now, this might sound like a technical detail, a philosophical nicety of interest only to specialists, but it has enormous consequences for what happens inside black holes. Remember the singularity problem. In classical general relativity, a collapsing star compresses to infinite density because space is infinitely divisible. The matter can always be squeezed into a smaller and smaller region. There's no floor, no bottom, nothing to stop the collapse. But if space is quantized, if there's the smallest possible chunk, then the collapse has to stop. The matter literally can't be compressed below the Planck volume. There's a physical barrier built into the fabric of reality itself. And when the collapse hits that barrier, something has to give. Let me try to give you a picture of what happens at the bounce. It's necessarily going to be incomplete. We're talking about physics at scales so small that our usual intuitions completely fail, but I think the picture is valuable nonetheless. Imagine a star collapsing. In the early stages, the physics is straightforward. Gravity pulls the matter inward, the star gets denser. The electrons get pushed into the atomic nuclei, turning protons into neutrons. You get a neutron star, an object so dense that a teaspoon would weigh billions of tons. If the star is massive enough, even the neutrons can't resist the gravitational pressure. The collapse continues. The density keeps increasing. Space-time curves more and more sharply around the collapsing matter. An event horizon forms that point of no return we talked about, but the matter inside doesn't know about the event horizon, doesn't care about it. It just keeps falling, keep compressing, keep increasing in density. Now, in classical general relativity, this process continues forever. Density goes to infinity, space-time curvature goes to infinity, time itself ends at the singularity. But in loop quantum gravity, something different happens. As the matter approaches Planck density, about 1096 kilograms per cubic meter, unimaginably denser than anything we encounter in ordinary physics, the quantized nature of space-time becomes important. The matter starts to feel the atoms of space. It can't compress further. It's hitting the floor. And here's the crucial part. When matter reaches this maximum density, the effective gravitational force changes sign. It becomes repulsive. I want to emphasize how strange this is. Gravity in our everyday experience is always attractive. Masses pull toward each other. That's what gravity does. We've never seen gravity push anything apart. But at Planck density, quantum effects dominate. The mathematics of loop quantum gravity shows that these quantum effects generate an effective repulsion that overwhelms the classical attraction. The collapse is arrested and then reversed. The matter bounces. Now, here's where it gets really interesting. Where does the matter bounce to? In ordinary physics, if you squeeze a ball and it bounces back into the same space it occupied before. It returns to where it came from. But the black hole bounce isn't like that. The matter can't bounce back through the event horizon, that's a one-way barrier. It can't expand back into the universe it came from. Instead, the bounce creates new space. The matter expands into a region that didn't exist before, a region that's causally disconnected from the original universe. Let me say that again because it's so strange. The bounce doesn't happen in existing space. It creates new space. The matter becomes the seed of a new universe, a universe that begins in an explosion of expanding space-time, much like our own Big Bang. You might be wondering, how can new space be created? Where does it come from? And this is where we have to confront one of the deepest mysteries in all of physics. The nature of space-time itself. In general relativity, space-time is not a fixed background. It's a dynamic entity that can stretch and shrink and bend. The Big Bang itself was an expansion of space-time, not an explosion into existing space, but an expansion of space itself. We're used to thinking of the universe as a collection of objects sitting in space, but that's backwards. Space and the objects in it are part of a unified whole. Matter tells space-time how to curve. Curved space-time tells matter how to move. They're not separate. They're aspects of the same underlying reality. The black hole bounce takes this idea to its logical conclusion. If space-time is dynamic, if it can expand and curve and change, then it can also branch. It can split off new regions. The matter falling into a black hole carries with it the potential for new space-time, and at the bounce, that potential is realized. This is deeply counterintuitive. Our brains evolved to navigate a world where space is fixed and objects move through it. The idea that space itself can multiply, can sprout new regions, goes against every intuition we have. But that's what the mathematics says. And at this point in physics, we've learned to trust the mathematics even when it conflicts with intuition. Now, I want to introduce a character to help make this concrete. Let's call her Gracie. Gracie is an astronaut, a very brave astronaut who's going to fall into a black hole. This is a one-way trip, of course. Gracie knows she's not coming back, but she's equipped with instruments and she's going to send us data for as long as she can. Gracie approaches the black hole. From her perspective, nothing special happens as she crosses the event horizon. She doesn't feel a bump or a jolt. She doesn't see a boundary. She just keeps falling. But her instruments start recording strange things. The curvature of space-time is increasing. The tidal forces are getting stronger. In a small black hole, these forces would tear her apart long before she reached the center. But let's say this is a supermassive black hole, billions of times the mass of the sun, where the tidal forces at the event horizon are gentle enough to survive. Gracie falls deeper. Minutes pass, then hours, then, well, time gets strange inside a black hole. The usual distinctions between space and time break down. But from Gracie's perspective, she keeps falling toward the center. And then something extraordinary happens. Instead of hitting a singularity, instead of being crushed to infinite density, Gracie experiences the bounce. Her instruments record a moment of maximum density, incredibly high, but finite, followed by an expansion. She's no longer falling, she's expanding. Space around her is growing. From Gracie's perspective, she's just experienced something like a Big Bang. She's in a new universe, a baby universe born from the black hole she fell into. And that universe is expanding, potentially capable of developing its own structures, its own galaxies, its own complexity. Now, Gracie can never communicate this to us. She's behind the event horizon. No signal can escape from our perspective. She just disappeared into the black hole and was never heard from again. But from her perspective, and this is the mind-bending part, a whole new cosmos has opened up. I want to pause here and address something that I'm sure is bothering some of you. This sounds like science fiction. It sounds like speculation piled on speculation. How can we possibly take this seriously as science? And I understand the skepticism. I really do. But let me explain why I think this is more than just wild speculation. First, as I mentioned earlier, the mathematics is rigorous. Loop quantum gravity is not a collection of hand-waving arguments. It's a detailed mathematical framework that has been developed over decades by serious physicists. The bounce scenario follows from the equations. It's not assumed, it's derived. Second, the bounce scenario solves real problems. The singularity is not a prediction of general relativity, it's a failure of general relativity. Any theory that resolves the singularities, making progress, is explaining something that was previously unexplained. The bounce does this. Third, and perhaps most importantly, the bounce scenario is consistent with everything we observe. We can't see inside black holes. We can't directly test what happens at the center. But the bounce scenario doesn't contradict any observation we've ever made. It fits within our existing knowledge. This is how theoretical physics often works, especially at the frontiers. You develop mathematical frameworks that resolve theoretical problems and make testable predictions. Then you wait sometimes for decades until technology catches up and you can actually test those predictions. We're in that waiting period now. But the work being done is genuine science, and the conclusions being reached are genuine scientific conclusions. Now, let me tell you about something that connects the bounce scenario to the very beginning of our own universe. Because if black holes give birth to new universes, there's an obvious question. Was our universe born from a black hole? Here's what we know about the Big Bang. About 13.8 billion years ago, our universe was in an incredibly hot, dense state. It was expanding rapidly. Space itself was stretching, carrying matter and energy with it. As it expanded, it cooled. Particles formed, then atoms, then stars and galaxies. But what happened before the Big Bang? What caused the initial expansion? Why was the early universe so hot and dense? These are the hardest questions in cosmology. And for a long time, the honest answer was, we don't know. General relativity predicts a singularity at the beginning, just like it predicts a singularity at the center of a black hole. And just like the black hole singularity, this cosmological singularity is probably not real. It's probably a sign that our theory breaks down. Loop quantum cosmology, the application of loop quantum gravity to the early universe, suggests a remarkable answer. The Big Bang may have been a big bounce. Before our universe was expanding, it was contracting. It was another phase of cosmic evolution, perhaps a previous universe, that collapsed down to Planck density. And at that maximum density, the quantum gravity effects kicked in. The contraction reversed, the collapse became an expansion. Our Big Bang was the bounce. The seed of our universe was whatever collapsed to create it, perhaps a dying previous universe, perhaps the interior of a black hole in some parent universe. We don't know the details. But the framework provides a coherent picture where singularities are replaced by bounces, where endings become beginnings. Let me push this idea a little further, because I think it has profound philosophical implications. If our universe was born from a black hole, and if our universe contains black holes that are giving birth to new universes, then we're part of a vast cosmic web, a family tree of universes, each connected to its parent by the black hole that birthed it, each spawning children through its own black holes. How far back does this go? Is there an original universe, a first ancestor in the cosmic genealogy, or does the chain extend infinitely into the past? We don't know. The mathematics doesn't tell us. It's possible that the chain is infinite, that there was no first universe, that universes have been bouncing into existence forever. This is hard to wrap your mind around. We're used to thinking that everything has a beginning. But infinity doesn't care about our preferences. If the equations permit infinite chains, then infinite chains are possible. Or perhaps there is a first universe, an uncaused cause, a spontaneous fluctuation in some primordial quantum state. Perhaps the question, what came before, eventually loses meaning. Perhaps at the deepest level of reality, time itself is emergent, and the chain of causation doesn't extend backward forever because time doesn't extend backward forever. These are questions at the very edge of physics and philosophy. We don't have answers. But the fact that we can ask them coherently, that we have mathematical frameworks within which they make sense, that's extraordinary. Now, I want to come back to something I touched on earlier. The idea that this cosmic evolutionary process might be subject to something like natural selection. This is an idea that physicist Lee Smolin proposed in the 1990s, and it's gained new relevance in light of the recent work on black hole bounces. Here's the basic concept. If universes give birth to new universes through black holes, then universes that produce more black holes have more offspring. And if the laws of physics in a daughter universe are similar to, but slightly different from, the laws in its parent universe, then over many generations, universes that are good at producing black holes will come to dominate. This is natural selection applied to universes instead of organisms. Universes don't compete for resources the way organisms do, but universes that produce more black holes produce more descendants. And whatever properties make a universe good at producing black holes will be reinforced over cosmic time. Now, here's what makes this idea interesting. Black holes are produced by stars. Stars are produced by galaxies. Galaxies are produced by the gravitational collapse of matter. And the amount of matter, the strength of gravity, the efficiency of star formation, all of these depend on the fundamental constants of physics. If you change the constants, the strength of the electromagnetic force, the mass of the proton, the cosmological constant, you change how many black holes a universe produces. Some changes would produce more, some would produce fewer, some would produce none at all. Smolin's hypothesis is that our universe, with its particular constants, has been selected over countless generations for its ability to produce black holes. The constants aren't random. They're the result of a cosmic evolutionary process that has been running for, well, possibly forever. I find this idea both beautiful and troubling. Beautiful because it offers an explanation for something that has always seemed mysterious. Why are the fundamental constants of our universe what they are? Why does the proton have the mass it has? Why is gravity as weak as it is? These seem like arbitrary choices, features of our universe that could have been otherwise. But if cosmic natural selection is real, they're not arbitrary at all. They're the result of eons of selection. Troubling because it's hard to test. We can't observe other universes. We can't measure their fundamental constants. We can't see the cosmic genealogy directly. The best we can do is ask whether our universe is optimized for black hole production. And that's a subtle question because we'd need to know how black hole production depends on the constants, which requires detailed calculations. Some of those calculations have been done. The results are suggestive but not conclusive. It does seem that the constants of our universe are close to optimal for black hole production, but there's room for doubt, room for alternative explanations. This is science at its most speculative edge, but it's not pseudoscience. It's a hypothesis that makes predictions that could in principle be tested, that fits within the framework of what we know. It's just very, very hard to test. Let me tell you about another implication of the bounce scenario that I find fascinating. It concerns the information paradox we discussed earlier. Remember the problem. Quantum mechanics says information is never destroyed. Black holes seem to destroy information. When they evaporate via Hawking radiation, the information about what fell in seems to be lost. The bounce scenario offers a resolution. The information isn't destroyed. It passes through the bounce and into the baby universe. From our perspective, it's lost because we can't access the baby universe. But from a global perspective, from a God's eye view that encompasses all universes, the information is conserved. This is philosophically satisfying in a way that other proposed resolutions aren't. Some physicists have suggested that the information somehow leaks out through the Hawking radiation, encoded in subtle correlations. But the calculations supporting this are controversial, and many physicists find them unsatisfying. The bounce scenario is different. It says the information goes somewhere real, somewhere physical. It's not encoded in subtle correlations. It's actually present in a new region of space-time. We just can't get to it. Whether this counts as conservation of information is partly a matter of definition. If you define our universe as everything that exists, then the information is conserved. If you define it as everything we can access, then it's not. The physics is clear. The interpretation is where things get murky. Now, I want to address something that might have been nagging at you. If the bounce creates a new universe, what does that universe look like? Is it like ours? Could it develop stars and planets and life? The honest answer is, we don't know. The details depend on exactly how the bounce works, how the properties of the parent universe transfer to the child universe, how the laws of physics might vary. But we can say some things. The baby universe would start in an extremely hot, dense state, much like our own universe, just after the Big Bang. It would expand and cool. If the laws of physics are similar to ours, particles would form then atoms, then given enough time, stars and galaxies. But would the laws be similar? This is where things get interesting. In some versions of the bounce scenario, the laws are exactly the same. The baby universe is just like the parent, born with the same fundamental constants, the same particle physics, the same rules. In other versions, the laws can change slightly at the bounce. Random fluctuations, quantum uncertainties could lead to small variations in the constants. The baby universe would be similar to the parent but not identical. If this second scenario is correct, then the cosmic natural selection idea becomes very powerful. Universes that are good at making black holes would have many offspring with similar properties. Over countless generations, the population of universes would evolve toward configurations that maximize black hole production. Our universe, in this picture, is not an accident. It's not a random draw from some space of possible universes. It's the product of eons of selection honed by cosmic evolution to be good at making stars and black holes. Let me bring George back into the picture to help illustrate something about the nature of these baby universes. George is a physicist in one of these baby universes. His universe was born from a black hole in a parent universe. Let's call it universe alpha, about 10 billion years ago. George doesn't know this. He has no way of knowing this. His event horizon separates him completely from universe alpha. From George's perspective, his universe started with a Big Bang. It expanded and cooled and formed galaxies. George was born on a planet around one of those galaxies' stars. He became a physicist. He's studying cosmology, trying to understand how his universe began. And here's the thing. George might develop the same theories we've developed. He might discover general relativity and quantum mechanics. He might figure out that black holes could create baby universes. He might even speculate that his universe was born from such a process. But he can't know for sure. He can't send a probe through a black hole and get data back. He can't communicate with universe alpha. The connection between his universe and its parent is real, but it's a one-way connection. Information can flow in through the bounce, but not back. George is in exactly the same situation we're in. He can develop theories, he can make predictions, but he